Morning. Hi, so my name's Matt Bostock. I'm here to talk to you about how we're using Prometheus to monitor Cloudflare's planet scale edge and also our internal services. So I work on the platform operations team at Cloudflare. We're focused on long-term improvement works to our infrastructure, both the infrastructure that supports the edge and also internal services. I also organize the Prometheus meetup in London. So what I'm going to talk about today, this is going to be a fairly dense talk because it's kind of covering work by multiple people and multiple teams over 18 months. I'm going to go through what is Prometheus, why you might want to use Prometheus, what our monitoring architecture looks like, and also approaches for reducing alert fatigue and pushing through engineering changes across a large organization. So I'm going to tell you the key takeaways from this talk so that you can bear them in mind as I go through the talk. So one of the things to keep in mind is Prometheus is the new gold standard for monitoring. I hope I can convince you of this. There are good alternatives to Nagios. Nagios is a good tool, but there are alternatives. Monitor within the same failure domain. So when you're doing your monitoring, you want your monitoring and alerting to be as close as possible to the thing that you're actually monitoring. Good monitoring doesn't happen for free. It requires a lot of investment, and it does take time. And related to that, good visibility also takes time. So you need training. You need to spread the word, get people invested in your monitoring solution. And this is not just specific to Prometheus. This is general. And also, monitoring is an interaction with humans. So you need to consider what the user journey is for the people that are receiving the alerts. How do they react to them? What pain points are they suffering? So what is Prometheus? So Prometheus is a monitoring system using metrics, started in 2012 by Matt Proud, incubated by SoundCloud. It's now got a governance structure. It's a hosted project of the Cloud Native Computing Foundation, the CNCF. It has a time series database at its core. It's designed for reliability, so all of the metrics data is stored within a single server. And it has a strong community. So just on the main repository for the Prometheus server itself, there are over 160 contributors, and the ecosystem is growing. So why might you use Prometheus? So I mentioned reliability. It's a single binary. I managed to even get it compiled on my Chromebook with a separate process for alerting. There's no clustering within Prometheus. There's no shared state between Prometheus servers. And that's intentional because you want your monitoring to be more reliable than anything else. It uses a pull rather than a push model because your monitoring should know what systems should exist. And related to that, it has a dynamic service discovery mechanism. So it has multiple service discovery mechanisms built in. The simplest of those is just reading a JSON file. And the more complex ones are DNS service discovery, console, or Kubernetes. Prometheus also has a really succinct query language that is read-only called PromQL. And it makes it really easy to view your data. And it's a bit easier than, say, SQL, and a lot more succinct. Prometheus is also multidimensional, which kind of distinguishes it from Graphite, if that's what you're familiar with, in the sense that every metric or every metric can have multiple labels. So, for example, if I want to count how many HTTP 500s I got, I can have a status label, and I can distinguish each different HTTP code. I also have a job label, so that's the name of the service, and an instance, so that could be a server, it could be a container, whatever's most useful to you. And you can aggregate on these labels, so it makes it really easy to filter your data. OK, so what's the scope of the problem we're trying to solve? What are we trying to monitor? So we're using Prometheus for monitoring. I think that's quite important to state. So Prometheus is really designed for monitoring. You do get metrics as well, but we're not using Prometheus for long-term storage. So by monitoring, I mean alerting on critical production issues, incident response, post-mortem analysis. And for long-term storage, we're currently using OpenTSDB. We're looking at reviewing that, but for now, this talk is really focused on using Prometheus for monitoring. So what are we trying to monitor? So Cloudflare has a large anycast edge network. We're in over 116 locations worldwide. We receive a lot of requests. That's both HTTP and DNS, so 5 million HTTP requests per second. And we're serving content for 6 million websites. So HTTP and DNS, we're a large managed DNS provider. And all of these features are supported by internal services, which also need monitoring. And there are analytics backends. Customers want to see how well their websites are performing. So there are a lot of internal services that need to support this edge. So this is what our Prometheus deployment looks like. We have 188 Prometheus servers or Prometheus instances currently in production worldwide. We have 4 top-level Prometheus servers, so that's two pairs of highly available top-level servers. The maximum size of data from Prometheus on any of those servers is 250 gigabytes. On the largest server, it has 4.8 million time series, and by time series, that's the combination of metric name and label names and values multiplied. And the largest server is ingesting 72,000 samples per second. We're still deploying the service, so that's going to grow over time as more applications use Prometheus. And we're running this on RAID 10 SSDs. So what does our edge architecture look like? This is really important to understand why we're monitoring our service in the way that we are. So our edge architecture uses routing via anycast. So as a person visiting a website that is using Cloudflare, you're going to reach the nearest point of presence that's geographically closest to you, roughly, depending on how many. It's using the number of network hops. That's usually the closest to you geographically. And each of these points of presence is configured identically. So from a monitoring standpoint, that's really important to note that each of these points of presence run the same services. They are different sizes, but essentially they're identical. And each point of presence is identical. So if we have a problem in a given point of presence, we can stop advertising the BGP routes for that particular location, and the traffic will shift elsewhere. So the primary services we have in each point of presence, these are the main ones. HTTP, DNS. We have a replicated key value store called Quicksilver, which is used for replicating customer configuration, and services such as attack mitigation as well. So that's the edge. In the core data centers, we also have a lot of analytics. We have logging, so enterprise customers can access their logs. We have audit D for security, HTTP errors from our services at the edge, application and operational metrics, and internal and customer-facing APIs. So there's a lot to monitor here. So some of the services we run in our core data centers, Marathon, Ceph, ClickHouse, Postgres, there is a lot to monitor. So a little bit about Prometheus and Prometheus queries. So there are really two main parts to Prometheus. There's the metrics exposition format, which is great in itself, and that's just a way of having your services expose metrics. There's actually some work being done to standardize that format as part of the open metrics standard. And then there's also the Prometheus data model, so how your metrics are structured. Then there's also the Prometheus server itself, and so you can use Prometheus metrics without actually running the Prometheus server. So a little bit about Prometheus queries and the data model. So querying multi-dimensional metrics is incredibly powerful, and it allows you to aggregate metrics in ways that are really easy. And so the Prometheus data model is a major advantage. So here's a fairly simple one. If I want to see the RAID health per server as a percentage, I can take the number of disks active in the RAID array, divide it by the number of total disks, and then times it by 100 to get a percentage. And I could turn this into an alert, or I could show it on a dashboard. If I want to know how many distinct kernel versions are deployed across the fleet, there's a metric called node uname info. It gives me the kernel version when it was built. And so I can see how many different kernel versions you're running across the fleet. This one's a bit more complex. This metric tries to emulate r_await from IOstat, which is the time to serve disk reads on average. So you get a lot of quite advanced, very useful system metrics for free from Prometheus' standard exporters as well. So that's the query, what the queries can look like. But what about metrics for alerting? Well, using metrics for alerting gives you a great amount of flexibility. And I think once you've got used to this mindset, it is quite a shift. I think it's really hard to go back. So here, for example, if I want to alert whenever the percentage of 500 errors for my HTTP service goes above 0, I can sum the number of 5xx errors, divide them by the total number of requests, times it by 100, and then whenever that number goes above 0, I can fire off an alert. And you can slice this data however you wish to do it. This is a more complex query. In general, try and keep your queries as simple as possible, because people have to read them later. But this is an example of the power of the query language. So if you want to alert when your HDFS cluster is unbalanced, and you need to run the balancer because some nodes in the cluster are using significantly more disk space than the other nodes in the cluster, you can alert on that. And so in this case, we're actually returning the number of servers that are out of balance. So it looks quite complex, but imagine if this was SQL. So PromQL is a read-only language, which means that there's no select keyword, for example. So it actually simplifies things quite a lot. OK, so what does our Prometheus architecture look like? So before we were using Nagios, it was a single instance running in a single location. We'd tuned it as far as we could. There's a great page in the Nagios documentation that explains how to tune it for high volumes. And I looked through, and we'd actually applied all of those all of that advice in that page. We were also using Nagios as an alerting backend or front end, depending on how you look at it, for a custom metrics pipeline. So we were sending the data into Nagios and then using Nagios to do the alerting. That worked pretty well for us for a long time, but it was complicated to configure new alerts. The metrics pipeline and the integration with that was quite complex, and there's a lot of moving parts. We had no versioning of alert definitions. It was quite difficult for product teams to add their own alerts, and we had no grouping of alerts. So we had a lot of alert noise. Some time ago, some people started looking at they looked at spiking new different alternatives. One of them was from Stack Overflow, Bostock, I believe it's called. The other one was Prometheus. And so we started using Prometheus as an alerting front end for the same metrics pipeline. So we're kind of using it in the same way that we're using Nagios, but we were using it in a way that Prometheus is not really designed to be used. And it didn't really fit with the Prometheus semantics. It was fragile, and there was some single points of failure. So we looked at how could we deploy Prometheus in a way that it's intended to be used. We wrote a specification. We published it on the wiki. We got involvement from multiple teams for people to review it. We got a lot of comments, so it was a long specification, a lot of comments. This thing is hard, right? It's really hard to push through changes, especially when it's a large change, because monitoring is really important, right? Nobody wants it to break. And so one of the sources of pushback was to use the pull model rather than the push models, because we already had this metrics pipeline, so why change that? Well, the point was that the metrics pipeline was designed for reliability. And yes, your monitoring needs to be reliable as well. But what you care about most in your monitoring is, I want to know what's broken right now. I don't want to find out about it 10 minutes later. And so that was really the argument for us to use the pull model. We're still using push for metrics for long-term storage, but we're using Prometheus as it's intended to be used using the pull model. And so over time, this took some time to get some consensus and some agreement. And we also, once we had that agreement, we had to convince the application teams to start instrumenting their applications. And that also takes time. So in some cases, it was a case of creating a ticket to suggest that this application should be using Prometheus metrics. And it took some time for that to turn into an epic, for that to be eventually prioritized by the team. And sometimes you have to kind of plant the seed early and keep talking to people and highlight the benefits for them. So how do we deploy Prometheus? So inside each location, we run the Prometheus server, the Prometheus instance on the management node. And depending on the size of the point of presence, we might have one management node or multiple. And for simplicity reasons, all of those management nodes are configured identically. So if there are 5 management nodes in a point of presence, we'll have 5 Prometheus servers. And each of those Prometheus servers is independent. There's no shared state. And they all send alerts independently as well. The Prometheus server knows which service to contact because it pulls. We have a Go daemon that runs on the management node next to Prometheus, and it pulls information from an API about which service should exist. It writes that as a file to disk in JSON format, and Prometheus then reads from that. So it's a really nice example of how the file service discovery mechanism can be really simple to work with and to integrate with. So each dot on the map that I showed you before runs at least one Prometheus server, up to 6 in one location. And the majority of our alerts come from the POPs themselves. So we want to generate the alerts as close as possible to the thing that is being monitored. So within the same failure domain, essentially within the same LAN, within that POP. So how do we get the metrics? So metrics are exposed by Prometheus exporters. An exporter is just a process. You usually have one exporter, one instance of an exporter per thing that you're monitoring. It speaks HTTP. It answers on /metrics. So if you curl /metrics, you will see the metrics. There's a large exporter ecosystem, a lot of them are already written, but you can also write your own, and there are excellent guidelines on how to write your own. So this is an example. This is the Prometheus node exporter, which is an official exporter, part of the community. This is just running on my laptop, and here I have some CPU metrics. I'm curling localhost /metrics, and I can see this is what the metrics look like. They're in plain text. It's very, very easy to instrument your applications. You only need to have your application speak HTTP and output some plain text. So the diagram that I showed you before is actually a little bit more complex because we have multiple exporters running on each server. So each Prometheus server knows which exporters exist on which server, and it's sending HTTP requests to them to collect the metrics. But actually, it's a bit more complex than that because we're running Prometheus in high availability, which means that we have multiple Prometheus servers running. They're all independent, and each of them are scraping the same metrics from the same set of servers. If one of those Prometheus servers fails, the other one keeps going. We don't have to worry about it. They'll keep alerting. So now on to federation. So we have all of these servers distributed across the world, each independent. But how do we get a global overview of what our metrics look like? Well, we federate select metrics up to what we call our top-level Prometheus servers, which are in our core data centers. And we do that so we can have a service-level overview of how our systems are performing. Because Prometheus is limited by the size of the server that you put it on, you don't want to federate all of your metrics, so we federate just a subset, just enough for us to have a global picture of what's happening. So in this example, I'm federating from 3 points of presence, but in fact, we federate from all points of presence up to the top-level Prometheus servers. But in actuality, those top-level Prometheus servers are collecting metrics from every single Prometheus server in every single data center. And then we run those top-level Prometheus servers in high availability as well. So again, they're independent. There's no shared state. There's no shared storage. And if one of them goes down, the other one can continue alerting. You can continue querying it. And we haven't done this yet, but we're also looking at putting a pair of those top-level Prometheus servers in the US and another pair in Europe, which means that we then have redundancy between regions as well. So a little bit about our retention and sample frequency. We scrape metrics every 60 seconds. Due to the large sample size that we have, we found that works pretty well for us. We could reduce that on some metrics to catch very brief spikes that can occur. But for now, just while we're sort of getting people on board and rolling this out, we found that this works really well. We collect federated metrics every 30 seconds, because then we avoid waiting up to 2 minutes before we can collect metrics, because you're essentially going down a tree at that point. There's no downsampling because Prometheus doesn't support it. The metrics storage format is really efficient. So there's no downsampling. Every data point that is collected is stored. And we keep those metrics for 15 days, which is just long enough for us to do post-mortem analysis, incident analysis, and monitoring. And over time, we might increase that, but for now, we wanted to keep it low. We initially set it at 2 days so that we don't raise expectations too high, and then we find out we run out of space when we have all of the services using Prometheus. So these are the exporters that we have deployed on across our whole fleet. So we have the system level metrics from the node exporter. We use the black box exporter for black box monitoring. That's hitting a network endpoint and seeing if it's up. And that can also give you information such as SSL expiry dates. We use mtail, which allows you to match logs. That's really good for when you can't instrument an application because you can't change the source, or you just don't want to, maybe it's the kernel. You can match patterns in log lines and increment counters based on how many times you've seen that match. And then we use the advisor for namespace metrics, so metrics about containers. When you're deploying exporters, use one exporter per service instance. It's an anti-pattern in Prometheus to funnel all of your metrics through one single process. It's a single point of failure, and if it fails, it's really hard to debug, and it's really hard to troubleshoot. So separate your concerns. If you're monitoring Postgres, but you also want to run some custom queries on your Postgres server that are maybe like application level metrics that you want to monitor, use separate exporters for those different concerns, and deploy them within the same failure domain. So if you're monitoring your Postgres server and that's running on bare metal, run the exporter on the same bare metal server. If you're running something in Marathon, then run your exporters in Marathon on the same cluster. So what about alerting? So I mentioned all of these Prometheus servers are alerting independently, so how do we not just get bombarded by alerts? Well, Prometheus uses the Prometheus ecosystem has a separate service for alerting. That's called the Alert Manager, and it deduplicates the alerts that it receives from Prometheus. So all of these points of presence will send alerts into Alert Manager, and Alert Manager will group them, and we group them by POP, and we group them by alert name as well. And so that reduces the amount of alert noise that we receive. We're also looking at deploying another Alert Manager in a separate region. I think Alert Manager at the moment is the weakest link in our monitoring chain. And so Alert Manager supports a high availability mode where it will gossip between the two instances about which notifications have already been sent. And if the gossip protocol fails, if the Alert Manager instances can't talk to each other, they'll just send the alerts anyway. So worst case scenario, you get duplicated alerts, but better duplicated than nothing at all. So when you're writing alert rules, test your query on past data. So make sure it's not going to alert as soon as you deploy the alert. Test your query and see how flappy the alert will be. Make the alert name really descriptive, so don't just call it RAID array, call it RAID health degraded. Remember, there are humans that have to respond to this, so make it as easy as possible. Use an adjective or an adverb. Add an alert reference so that the person responding to the alert knows how to mitigate the problem, that there are actually steps that they can action to solve the problem. And make sure that the alert is actually actionable. Don't send alerts that people can't fix, because they're just going to start ignoring them, and people will start filtering out that alert noise. And keep it simple. When you write an alert, people have to read it later, and often the person reading it is the person responding to on call, because they're trying to figure out, why is this thing alerting? Is it really something I have to worry about? So keep the alerts simple. This is an example alerting rule we have. So this is the RAID health example. We're sending RAID health alerts into Jira so that we can triage them as part of a backlog, because you don't need to know immediately if the RAID health is degraded, because you can come to it a little bit later. We can include the metric value in the summary. We can use the labels. We can template the dashboard link so you can link straight to the server affected, and include an alert reference link as well. When you're writing dashboards, use drill down dashboards for additional detail. Template your dashboards using labels. You can even add the data source as a variable, so you can select between different Prometheus servers in your dashboard, and use dashboards as living documentation. So one of the things we did was use the diagram plugin for Grafana, which uses mermaid syntax, to actually add architecture diagrams to dashboards. And this can be the first thing that, when an alert goes off, this could be the first thing that somebody sees. We're still playing with this. It's a bit experimental. But for example, you can see how many alerts are firing for a given component. And so when you're responding to an alert, that's a really nice way to see where is the problem. And so the most important thing about this is really remembering that monitoring is an interaction with humans. So you need to understand the user journey of the person that's responding to the alerts. Not everything is critical, so make sure that your alerts are actionable and that you use severity levels as well, so that people can understand how important something is and what the impact is on users as well. So include the impact in the alert reference. Pick the right channels. So we send a lot of alerts to HipChat. We can also view them in a dashboard, which we've open sourced. I'll show you later. But if the issue is if it's going to cause a problem later, but it's not causing a problem right now, create a Jira for it, and that allows teams to triage those issues and work on them as part of a backlog. Alert over symptoms rather than causes. I'll let you Google that, because it will explain it much better than I can in the time I have. An alert on services rather than machines. So if you alert on individual machines, if you alert on individual causes, you're going to have a lot of alerts. So alert on symptoms, you're going to have much less noisy alerts, and err on the side of alerting less rather than more. So what about monitoring your monitoring? So each Prometheus server monitors all other Prometheus servers, both within the POP and at the top level. And the top level Prometheus servers also monitor the Prometheus servers in the data center. So it's essentially a mesh monitoring for our own monitoring. For Alert Manager, we monitor 2 metrics. We monitor if Alert Manager is down using the Prometheus up metric. And we also, if we are receiving alerts, but we're not sending any out for a period of time, given our size, then that's quite a reliable indicator that there's a problem. So in this case, we actually use Grafana to alert us, because it's out of band from Alert Manager, because if Alert Manager's down, how are we going to receive the notifications? This is the only thing we use Grafana for, because we want to consolidate around Alert Manager, but it's a quick and easy way to get notifications or a page when Alert Manager is down. So this is what it looks like. You can see we actually hit a deadlock in Alert Manager in an earlier version, and we weren't sending notifications for a very brief period. Another thing we do is we actually run a drill at the start of each shift. So we have on-call shifts of 8 hours, and at the start of a shift, we'll fire a synthetic alert that goes all the way through to page duty and pages the individual that is on call for that shift. This won't work for every team, it won't work for every company, but we found it useful because it tests that the PagerDuty API key hasn't been reset, it tests that the person's phone is on, that they know they're on call, that their phone number hasn't changed, that they have cell phone reception, and we found that works really well. And it also tests that your alerting pipeline is working. So we've had a number of teams add, because our configuration is now in revision control, we've had a number of teams now add their own channels for alerting, so they can receive alerts about their services. And this is what our alerting tree looks like, and each kind of branch of these each branch is a grouping of teams essentially. So we also send alerts into Jira alerts. As I mentioned, we've adapted Fabian's Jira alert service for this. So this is on GitHub. And this allows better prioritization of less imminent issues. This is what it looks like. If the issue reoccurs, we reopen the same ticket to avoid creating duplicates. We're looking at if the issue hasn't recurred in a couple of days, then opening a new ticket and making this a little bit more usable. But so far, it's working really well for us. We also wrote a service called Alert Manager to ES, which sends our alert data into Elasticsearch, which means that we can then graph it in Grafana. So this is the number of alerts received over time for a given team. I'm afraid it's blurred out because I don't think I can share the numbers with you. But we can see for this team how many HipChat notifications they got, how many pages they got, which alerts were the noisiest, which data centers were the noisiest, and what was the long-term trend over time. So you can see when a team had a particularly bad week, and use this data to try and iterate and improve your alerts. We also created a dashboard that I mentioned called Unsee. This is open source, and it allows you to visualize your alerts like this. So I highly encourage you to check that out. And we contributed to Alert Manager to add a CLI tool so that you can add silences using the command line. Okay, so what are the lessons learned? We had a number of pain points. I'm not going to go into the detail now, but they are covered in the PromCon videos, which are going to be published soon. I gave a talk with the same title as this, and my colleague Lorenz gave a talk about Quicksilver. Most of these issues are really configuration issues specific to us. The last two, self-inhibiting alerts and cardinality explosions, they could affect anyone. But I recommend that you see the PromCon talks for more details. And these are being worked on. Standardize on your metric labels early. So if you're doing black box probing, try and figure out how you're going to set the labels for the source versus the target. So where your probe is originating from and what you're hitting. Also, standardize on environment labels, how you separate clusters, and how you separate different instances of the same app deployed in different roles. The really key thing is to be open and engage other teams early. So solicit reviews, give talks, documentation. This is stuff we're still working on. This stuff is hard. It doesn't come for free. It needs time. Highlight the benefits for individual teams and engage them early. And get backing from tech leadership and management so that you can prioritize adding the instrumentation and shifting to the new system. Keep iterating. So learn from your alert data. Learn from the things you've collected. and empower staff so that they can improve their own experience. And remember, keep the person that's responding to the alerts in mind. I'm going to go through this really quickly because I'm running out of time. But we still got a lot more to do. We've removed 80% of our Nagios alerts. This does take time. Prometheus 2.0 will reduce the memory requirements and the disk I/O requirements for us, and also handle metrics churn, so I recommend you try it out. I'm going to go through these and just say, if you want any more further information, check out the blog, the Cloudflare blog. We're going to be talking about this in more detail on there. Check out our GitHub organization where we've open sourced those tools, and try out Prometheus 2.0. It looks really great. And if you have any questions, I'm available on Twitter. Thank you very much.